Now we take the problem 69 of your textbook. This problem says a uniform rod is pivoted at its upper end and hangs vertically. So there is a rod, uniform rod, its mass length, nothing is given. We have to assume its mass length, etc. This is a uniform rod. The hands is pivoted at its upper end. That means here it is pivoted. That means the rod can swing left or right like this. It is displaced through an angle of 60 degrees. That means the rod is displaced to an angle of, let me take this rod a little bit away so that I have space for drawing. This is the rod. Say this is the rod. And it is displaced through an angle of, this angle is more or less a 60-degree angle. It can, then to form an arc here. So it is displaced through an angle of 60 degrees. This rod is displaced by an angle of 60 degrees. This is 60 degrees. And then released. Now it is released. If it is released here, of course, this will start moving in this direction. This direction. Find the magnitude of the force acting on a particle of dm at the tip of the rod when the rod makes an angle 37 degrees. So now the rod makes an angle of 37 degrees. This is another position of the rod. This is 37 degrees. We have to find out the force acting on a particle Tm at the tip of the rod at this point. That means a particle here. Now here, I want to give a caution to you that the paper setter who set this question, he has mentioned dm. That means is considering of differential calculus method, infinitely small particle, but the particle really does not exist there. I mean, there is no additional particle attached to the end of the rod. If there is an additional particle attached to the end of the rod, then its mass and the mass of the scale, everything has to be calculated. But it's a imaginary particle dm at the end of the rod. Practically, we have to find out the force acting at the end. Now, what are the forces? The forces acting here is actually a tangential force. Tangential force like this, which is equal to mass into tangential velocity v, and this has a centripetal force towards the center of rotation, which is equal to mv square by r. Now we have to find out the points. Obviously, whenever you handle such a point, you have to always consider the center of mass. You have to always consider the center of mass. We have to consider when the scale has dropped from 60 degree to 37 degree, how much the center of mass has dropped. Look, here, if you draw a horizontal line, you come here, this is L by 2. So this distance is L by 2. This distance is L by 2 cos 60. This is L by 2 cos 60. And if you draw a line here, this is L by 2 cos 37. L by 2 cos 37. So how much is the drop of the center of mass? This drop. So drop of the center of mass. So center of mass has dropped by the center of mass. The center of mass has dropped by a height of L by 2 cos 37 minus cos 60. So what is the potential energy lost by the rod? So potential energy lost by the rod is equal to L by 2 into mass of the rod. We consider mass of the rod M, G, cos 37 minus cos 60. Here I have considered mass of the rod, mass of the rod is equal to M I have considered, and length of the rod I have considered L. This is the consideration I have taken. So if this is the loss of potential energy, same is the gain of potential energy. So gain in kinetic energy. Gain in kinetic energy is the same amount. That means mgl by 2 cos 37 minus cos 60. Same is the gain in the kinetic energy. Also, we know kinetic energy is half I omega square. Also, we know kinetic energy. We are, of course, talking about rotational kinetic energy. Half I omega square. So if we can find out I, we can find out omega. Right? Now, half I omega square, kinetic energy is equal to half I omega square. This half I omega square is half. What is moment of inertia of this rod, which is rotating at one of its end, is 1/3 ml square. From standard formula, ml square by 3 into omega square equal to ml square omega square ml square omega square by 6. That means this ml square omega square by 6 is equal to this mgl by 2 cos 37 minus cos 60. So omega square ml, not omega square. Directly you cannot jump, you should not jump the stages. So ml square omega square ml square omega square by 6 is equal to 1/3 ml square omega square ml square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega square by 6 is equal to 1/3 ml square omega mg L by 2 cos 37 minus cos 60, and from here our m and m gets cancelled. 2 gets cancelled with 6. We are remaining with 3. We are left with 3. And L and L square cancels. We are left with L. So what we are left with is, what we are left on the left hand side, we have omega square. So we take omega square. This 3 goes to the right hand side. So it is 3g divided by L. 3g divided by L. And cos 37 minus cos 60 is a 0.8 minus 0.5 minus 0.5. This becomes, if we calculate, 0.9 G by L. This is one relation we have got. We have got the value of omega square. In fact, we don't need the value of omega. So we shall not do the square rooting. We shall leave it there. Omega square is 0.9 G by L. Now, let's go to the next point. Let us say, when the rod is at this 37 degree, when the rod is at 37 degrees, then let's look into it. There is a mass mg works in this direction. And this mass mg is creating a torque on the rod, and with this distance from this perpendicular distance from the fulcrum. This perpendicular distance we know will be actually L by 2 sine theta. This particular distance is L by 2 sine theta. So torque produced by mg is mg is L by 2 sine theta, not sine theta, sine 37. L by 2 sine 37 degree. So we come, when the rod is at 37 degree, its mass applies a torque through the center of mass. And this torque is equal to how much? Torque is equal to always force multiplied by the perpendicular distance, right? And the force is mg, and perpendicular distance is L by 2 sine 30 cos sine 37. L by 2 sine 37 degree. It is equal to mg L by 2 mg L by 2, and sine 37 is 3 by 5. This is equal to 3 mg L divided by 10. So this is the torque applied. Now this torque will create an angular acceleration. This torque creates an angular acceleration alpha. Say it is alpha. This torque creates an angular acceleration alpha, and we know torque is equal to moment of inertia multiplied by the angular acceleration. Or in otherwise, angular acceleration equal to torque divided by moment of inertia. So angular acceleration alpha is equal to, what is the torque? 3 mg by L. 3 mg by mgl by 10. 3 mgl by 10. And moment of inertia, again we know moment of inertia is 1/3 ml square. So 3 goes to the numerator and ml square. This makes it, this m and m gets cancelled. So this makes it 9. This makes it 9 by 10, that is 0.9, 0.9 G by L. This makes it 0.9 G by L. Once we have angular acceleration, we can find out this tangential, say this tangential acceleration is A, right? Therefore, tangential acceleration is, tangential acceleration is, so tangential acceleration A of the particle dm. Once again, I remind you, dm, the way the question has been set, dm is not really there is any new particle. It's a hypothetically considered infinitely small particle at the tip. And so tangential acceleration A is equal to alpha r is equal to alpha into length of the rod is L. A is equal to alpha L, and alpha already we have found 0.9 G by L, 0.9 G upon L, that multiplied by L, so it is 0.9 G. If we know the tangential acceleration A, then we know the (0.9 G). If we know the tangential acceleration A, then we know many things. Then force on dm or force on dm is actually mass into acceleration. So tangential force on dm, so tangential force on dm is equal to mass into acceleration, is equal to mass into acceleration, is equal to its mass is dm, and tangential acceleration is 0.9 g multiplied by 0.9 g. Now, what is this is, as we said at the very beginning, it has got a tangential force and a centripetal force. What is the centripetal force, you remember? It is mv square by r, where r is the radius of rotation. And the centripetal force on dm is equal to dm v square. We have not determined the tangential velocity. We have only determined tangential acceleration. So dm, we write it dm v square by L. From here, we shall be able to find out it is dm by L. V is equal to, we know it is omega r. That means here it will be omega square L square. This will be equal to dm omega square L. Dm omega square L. Now, omega square we have already found. Let us find where is omega square. Yeah, omega square is here. 0.9 G by L. Right? So, this is equal to dm multiplied by 0.9 G by L, that multiplied by another L. So this is equal to dm 0.9 G, 0.9 G. So there are two forces on this particle. One force is a centripetal force. This is 0.9 G dm, 0.9 G dm. There is another tangential force is incidentally same value, 0.9 G dm. So what is the resultant force acting on it? So the resultant force, the resultant force acting on dm, since both of them are same, so we have to just multiply it by √2. So it is equal to 0.9 √2 dm G. This is the answer. So this is the force on a particle, which if we assume a particle of small mass dm at the tip of the rod, then the force acting on the particle is 0.9 dm into G. Then we go to the next question.